So welcome everybody to the afternoon session, and the first speaker is Mina Aganagic, and she will talk about two mathematical applications of little string theory.
Okay, well, I want to thank the organizers for inviting me and for setting up such a wonderful conference for us. I guess they had it easy by the very fact that a conference is in Paris, but even taking that aside, I think it's wonderfully organized. Okay, so I'll tell you about work that I've done with my student, Nathan Hauzi, then later work with Andrei Oklenkov, and then I worked to appear with Edward Frankel and Andrei. So we'll take G to be a simply laced Lie algebra. There's the ADE classification. String theory predicts existence of a remarkable quantum field theory in 6 dimensions, labeled by G. This theory has 2-0 supersymmetry and is conformal. It's often called theory X. Now, theory X is, and that's how I'll call it for the rest of the talk, theory X is remarkable in part because it is expected to play an important role in mathematics. There is substantial evidence that theory X should have deep applications to geometric Longlands program and to knot categorification program. Now, an obstacle to making progress is the fact that the theory X is mysterious, even for physicists. It's mysterious because it's a theory without a classical limit. AGT correspondence, after Alde, Gayota, and Tachikawa, serves well to illustrate both the appeal of this theory and also the difficulty in working with it. So the correspondence states that the partition function of theory X on a 6-manifold, which is a product of a Riemann surface in R4, is a conformal block on the same Riemann surface of a conformal vertex operator algebra, which is also labeled by G, the same simply laced Lie algebra that X is labeled by. This algebra, in this case, is the doubly algebra. The correspondence further relates defects of the theory X inserted at points on the Riemann surface to vertex operators of the doubly algebra at the same points. Now, if one is to take the conjecture at its face value, it's hard to make progress on it. Because we do not know how to describe theory X, we cannot formulate or evaluate its partition function in any generality. We do not even have a well-defined statement of what the correspondence is, except in rare examples. Now, despite that, the physical implications of the AGT correspondence are incredibly important. Now, it turns out that there is an embedding of both sides of the correspondence into bigger theories, which allows us to make the correspondence both mathematically precise in a fairly general setting and to prove it. On the doubly algebra side, one replaces the ordinary doubly algebra by its Q deformation. This deformed doubly algebra is the one defined by Edward Frankel, who's here, and Nikolai Reshetikhin in the 90s. One replaces the 6-dimensional theory X, which is a point particle theory, by a 6-dimensional string theory which contains it, the little string theory. The little string theory is labeled by the same AD Lie algebra, G, as the theory X, and it can be viewed as a one-parameter deformation of it. The parameter one varies is the characteristic size of the string. In the limit, this vanishes. One gets a point particle theory. This point particle theory is theory X. Now, on each side of the correspondence, one replaces a theory with conformal symmetry with its mass deformation. And in both cases, the breaking of conformal symmetry is canonical. So the correspondence is between deformed doubly algebra, conformal blocks, and partition function of 6G little string theory on a 6-manifold, which is a product of C times R4, the same Riemann surface. And here we have to take the Riemann surface C to be either a cylinder or a torus. For this talk, I'll take C to be a cylinder since the torus case follows by additional identifications. So now it turns out that the partition function of G-type little string theory on C times R4 with an arbitrary collection of defects has a precise mathematical formulation. For codimension 2 defects inserted at points on the Riemann surface, the partition function of G-type little string theory on M6 is the equivariant K-theoretic instanton partition function of a certain G-type quiver gauge theory on R4. Which quiver gauge theory on R4 we get depends on the choice of codimension 2 defects. Now, the 6-dimensional theory turns out to localize to the theory on its defect. The quiver gauge theory one gets is simply the quiver gauge theory on the defects of a little string at points on C and filling the R4. So a consequence is that the partition function of 6D little string is the K-theoretic Nekrasov partition function of the gauge theory on its defect. Now, one gets the K-theoretic instanton partition function rather than the most obvious cohomological one due to a string effect. Because the little string is a string theory, one has to include the winding modes of strings which wind around the cylinder, and these turn the theory on the defects to a 5-dimensional gauge theory on S1 times R, and the circle here that you get is a T-dual of the circle in C. Now, recall that a choice of the defects in little string corresponds to choice of vertex operators of this deformed doubly algebra. So the mathematical statement of the correspondence is a relation between Q-deformed conformal blocks of the doubly algebra with collection of vertex operators at points on the Riemann surface and the K-theoretic instanton partition function of the corresponding G-type quiver gauge theory on R4. Now, this relation can be both spelled out in detail and proven. This fact, however, relies on using little string theory rather than theory X, to which it reduces to in the conformal limit. In the point particle limit, the theory on the defects, like theory X itself, has no known direct description. In particular, its partition function is not computed by any known, by instanton counting of any known kind. Okay, so in the rest of the talk, I will describe this correspondence in more detail, and then I will describe another related application to the geometric Longlands program. Okay, so to define this G-type little string on C times R4, one starts with 10-dimensional type 2B string theory on Y times C times R4, where Y is the AD surface is an AD surface singularity of type G. And remind you, we are taking C here to be a cylinder. Y, the AD surface, is asymptotically locally flat. It's obtained by taking a C-square mod gamma singularity and resolving it. And gamma here is a discrete subgroup of SU2, which is related to G by McKay correspondence. If one resolves the singularity at the origin of C-square mod gamma, you get a collection of vanishing 2 cycles, spheres, which intersect according to the Dinkin diagram of G. And in one's very first course on string theory, one learns how to formulate a 10-dimensional type 2B string in this setting. So there's certainly nothing mysterious about it. Now, the 6-dimensional little string theory is a 6-dimensional string one obtains by taking the limit of the full 10-dimensional type 2B on this, where one keeps only degrees of freedom localized near the singularity in Y. So you get a 6-dimensional theory on C times R4. Now, the limit that one takes involves sending the string coupling to 0. So type 2B string becomes classical. while keeping the characteristic size of the type 2B string finite. So this is a limit where we should be able to understand string theory in. This classical limit. Now, defects of little string theory originate as d-branes of the 10-dimensional string, which survive in the limit. In string theory on this geometry, the defects we need are d5 branes that are supported on two cycles in Y. They are at points in C, and they fill R4. The theory on the d5 branes is a quiver gauge theory with quiver, which is based on the Dinkin diagram of G, corresponding to the singularity. And in the quiver, for each node of the Dinkin diagram, so in such a quiver, for each node of the Dinkin diagram, one gets a pair of vector spaces, V and W, whose dimensions are D and M. These dimension vectors are determined by the classes of two cycles in Y, which support the d5 branes. Now, it's helpful here to recall that aspects of geometry of the AD surface are captured by representation theory of the Lie algebra. In particular, the second homology group, viewed as a lattice, where you get an inner product coming from the intersection form, is the same as the root lattice of G, and the second relative homology group is the same as the weight lattice. The vector space V comes from d5 branes supported on the 8th vanishing 2 cycle, which in turn corresponds to a simple root of G. And the vector space W's comes from d5 brane wrapping dual non-compact 2 cycle, which are labeled by fundamental weights of G. They are dual in this sense. The gauge group of the quiver gauge theory originates from the gauge theory on d5 branes supported on the compact 2 cycles. The matter fields come from intersections between branes, and the flavor symmetry group comes from gauge symmetry on the non-compact d5 branes. Now, for our purposes, we don't need an arbitrary quiver gauge theory, but we want those that describe defects of the 6D little string, which preserve 4-dimensional conformal invariance in the low energy limit. The answer can be stated as follows. Now, suppose I want to describe a single defect at a point of the Riemann surface in the conformal limit. So for this, I'll pick a collection of n+1 weights of G, where n is less than or equal to rank of the Lie algebra, such that every weight I pick is in the Y group orbit of some fundamental weight of G, and moreover, they sum up to 0. This is where one puts the conformal invariance. Now, if one wishes to get what's called a full puncture, the collection must, in addition, span the weight lattice. In particular, n is equal to the rank. Now, corresponding to this collection of non-compact of d5 branes, corresponding to this is a collection of cycles in Y on which d5 branes are supported. So this way, you get a gauge theory whose gauge group and global symmetry group are determined from the weights one has chosen. They're determined more precisely from this equation. Here, the flavor symmetry group depends on the number of the weights you picked from the orbit of a given fundamental weight. And then you use the equation to solve for D. The equation is simply a consequence of the fact that the weights sum up to 0. Now, if we consider several defects on C instead of 1, the ranks of the gauge and flavor symmetry group simply add. Now, Nekrasov formulated a K-theoretic instant partition function of this of any such quiver gauge theory on R4 as the equivariant Euler characteristic of an appropriate bundle of the moduli space of G instantons. I should say Nekrasov and Pestun as well. Localization lets one express this partition function as a sum over fixed points in instanton moduli space, labeled by rank G tuples of two-dimensional Young diagrams. This is a familiar story to many of you. So where one gets one two-dimensional Young diagram for each U1 factor in G. The important point is that contribution of each fixed point can be simply read off from the quiver as a product of contributions of the nodes and the arrows. And in the end, one sums over all the fixed points. So there's an algorithm. The answer depends on, in addition, on the instanton counting parameter, which I labeled e to the tau here, and on the equivariant parameters, because we compute this by localization. So the parameters q and t are related to rotations of the two complex plane in C2, where the gauge theory lives. Q for one copy of C and t for the other. The parameters, which I jointly call G, are associated to the maximal torus of the gauge group, and parameters, which I call X, are associated to the maximal torus of the global symmetry group. Now, all the parameters that enter the partition function have a geometric interpretation in string theory. The equivariant parameters, labeled by X, associated with the global symmetry group, are the positions on the Riemann surface of d fibrils that wrap the non-compact cycles. The equivariant parameters labeled by G, associated with the gauge group, are the positions on C of the d-branes on compact cycles, from which the gauge group comes from. And Q and T are associated, again, with rotation of R4, which is geometric in the 10-dimensional, in the 6-dimensional geometry. Now, tau, the related to the instanton counting parameter, comes from the moduli of y associated with the sizes of the vanishing two cycles, and also the moduli of the 6D little string. And as soon as we resolve the singularities of y and tau is non-zero, all the relevant dynamics of little string is localized to the d fibrils. So everything that comes from the bulk of little string theory is trivial, and all the interesting dynamics is localized on the d fibrils. Correspondingly, the instanton partition function we just explained how to compute is the partition function of a little string on M6 with the corresponding collection of defects. That's very simple. Now, let me describe the deformed doubly algebra corresponding to a simple Lie algebra G. In fact, for this part of the talk, we'll just pick G to be simply laced. So this doubly algebra is defined by Frankel and Reshetikhin in what's called a free field formalism. So one starts with a deformed Heisenberg algebra, which depends on two parameters Q and T and is associated to G. And this Heisenberg algebra has generators, one generator for each node of the Dynkin diagram, rather a whole integer worth of family of generators. And they satisfy commutation relations, which are given like this, where C is a deformed Cartan matrix. So if you set Q and T to 1, you get just the ordinary Cartan matrix, but otherwise it's a deformation that you can find in their papers. Now, for each weight of the Cartan subalgebra, we get a Fock representation of this Heisenberg algebra with state labeled by weight mu as a generator in the usual way. The doubly algebra itself can be defined as a set of vertex operators which commute with the screening charges, Q. Now, the screening charges are defined as integrals of screening currents, where the screening currents are given by this following explicit formula. Taking the limit where Q goes to 1, T goes to 1, where you keep Q to the beta, where you keep beta fixed, the deformed doubly algebra becomes the ordinary one, depending only on parameter beta. And the double algebra you get contains Virasoro algebra as a subalgebra, and its central charge depends on beta. General Q-conformal blocks of this double algebra are expected to be correlators of vertex operators with screening charge insertions computed of the following type, where the vertex operators are built out of Heisenberg algebra generators. Now, as of now, there is neither math nor physics definition of what it actually means to be a Q-deformed chiral vertex operator algebra. And correspondingly, Frankel and Reshetikhin in their paper did not define Q deformations of general vertex operators of the double algebra. They studied some, but not the most general ones, which we need here. Now, with Nathan, we show the following. So given a collection of weights, omegas, satisfying the conditions we stated before, where a weight omega is associated to a point x on the Riemann surface, one considers the following vertex operator, which is a product of vertex operators associated with individual omegas and x's. They're explicit formulas, and they have the following flavor. So the vertex operator for an individual weight is a normal order product of simple root and fundamental weight vertex operators, which naturally quantize the Lie algebra relations. Moreover, the vertex operator has the property that in the limit in which Q deformation goes away, so we said Q to 1, the vertex operator becomes the primary vertex operator of the conformal double algebra. So in taking this limit, you scale the positions of n plus 1 vertex operators to a single point, like this. And the relative speed at which they come together determines the momentum associated to the operator, if you know what it is. But anyhow, so they reduce the well-known primary vertex operators of the conformal double algebra. Now, one expects that there is a natural definition of what it means to be a deformed chiral vertex operator algebra, under which these are the natural primary vertex operators. As we'll see in the later part of the talk, this natural definition should be based on, at least for double algebra, should be based on quantum K theory and a class of three-dimensional gauge theories, which we'll discuss later. Anyway, with these vertex operators in hand, the Q correlators are in fact contour integrals because screening charges that enter them are integrals of screening currents. So to actually specify the Q conformal block, one has to specify the contour. Now, one can show that there are choices of that one can pick the contours in a way which we made explicit. These choices are parameterized by ways of splitting the numbers of screening charges, such that the conformal block, the Q conformal block, when evaluated by residues, equals the gauge theory partition function. The instanton counting parameter is identified with the weight of the Fermat module. And the choice of contour on the Q conformal block side enters in the choice of parameterization of G equivariant parameters that enter the instanton partition function the following way. Now, the relation, so as you can see, the relation between the Q conformal blocks of the double algebra on C and the K theoretic instanton partition function is simple and direct. The sum of the poles in the contour prescription to evaluate the conformal block, so computing this by contour integration, you get the sum over instantons term by term. So there's nothing magical going on. This is why one can prove. So we both have a statement and something that one can prove. And a provable statement, which we have. All right. So now the rest of the talk, I'll tell you about another application of little string theory to geometric Longlands. Now, before I get there, are there any questions? Yeah. The genus of the Riemann surface here is fixed. Riemann surface for us is a cylinder. You can generalize it to a torus, but that's probably where this story stops. These are completely generic conformal blocks. So you get completely generic conformal blocks in the following way. A single so everything starts out discrete, but to describe a single vertex operator in the conformal limit, you start with several defects to begin with on the Riemann surface. And as you take the conformal limit, you have to bring them together. Okay? So they come together at a point, and the rate at which they come together becomes the momentum, which is generic. Okay, so on to the Longlands. Now, geometric Longlands correspondence was formulated in the early 90s by Beilinson and Drinfeld. And in the same work, they explained that one can phrase the correspondence in the language of two-dimensional conformal field theory. This was further developed by Frankel, Fagin, and others. So let G and LG be a Longlands dual pair of Lie algebras. The geometric Longlands correspondence can be interpreted as the relation between conformal blocks on a Riemann surface C. On the electric side, one considers conformal blocks of affine current algebra associated with LG at a critical level, which is, in a sense, infinite coupling. And on the magnetic side, one gets conformal blocks of the doubly algebra, which we just met, but ordinary doubly algebra, in the classical beta to infinity limit. Aspects of geometric Longlands correspondence were proven in this context by Beilinson and Drinfeld already in the original paper, and in later works by Edward Frankel with Gaisgary and Villanen. Now, there are two ways you could try to generalize this. First, it's natural to deform away from the critical level, or equivalently to finite beta. Secondly, it's natural to replace the conformal chiral algebras by their Q-deform counterparts. The first deformation is the quantum Longlands correspondence. In the abelian case, it was proven by Polishchuk and Rothstein. For G is A1, some results were obtained by Fagin, Frankel, and Stoyanovsky, and Teschner and others. Now, it turns out that one can implement both generalizations, and in fact, it's easiest to do it at the same time. So in a joint work with Edward Frankel and Andrei Okumkov, we formulate quantum Q Longlands correspondence for any Lie algebra G and its Longlands dual LG. And we outline the proof of this correspondence in a simply laced case. So we conjecture the correspondence between deformed conformal blocks of the quantum affine algebra corresponding to LG hat at level K, and Q conformal blocks of a deformed double algebra, depending on Q and T, associated with the Longlands dual Lie algebra, G, where the parameters are related as follows. So T is simply H bar, and Q and H encodes the level in the following way. So the statement of the correspondence is the following. We take the Riemann surface C, which is a cylinder, with punctures at distinct points on the Riemann surface. And to a puncture, one associates a finite dimensional representation of LG. Now, for simplicity, we'll take the representations one picks to be one of the fundamental representation of LG, labeled by the nodes of its Dynkin diagram. On the electric affine current algebra side, one considers Q-conformal blocks of the quantum affine algebra, which take the following form. Phi corresponds to the finite dimensional representation, which we had attached to the corresponding point x. Phi's are so these are the conformal blocks that Igor Frankl and Nikolai Reshetikin defined when they defined long ago. These are simply the intertwiners of the quantum affine algebra associated with finite dimensional representations. On the magnetic doubly algebra side, one considers the Q correlator of this type, where V's are the magnetic degenerate vertex operators of the doubly algebra, which were defined, which you can find in the papers of Frankl and Reshetikin. Now, these are labeled by they're magnetic because they're labeled by fundamental co-weights of G, which by Longlands duality are highest weight of the representation of the electric group. And we pick, of course, that representation to be the one we attach to the point x. Now, one also inserts a number of magnetic screening charges. And which number one picks corresponds to restricting the quantum affine algebra block to a which a priori is valued in the tensor product of all the representations associated with the vertex operators you inserted to a subspace of the following weight. So m's are the numbers of v's, and d's are the numbers of q's. Now, the states one one computes the conformal block in, generate Verma module representations of both algebras, and lambda and lambda prime are not independent. They satisfy this relation, depending on the vertex operators you inserted. So there's basically one number to pick, one rank R vector, rank G vector to pick, lambda. Now, on both sides, to actually specify the conformal block, one needs additional data. On the doubly algebra side, we need to choose the contour of integration. On the affine current algebra side, one needs to specify the Verma modules in the intermediate channels. Now, it turns out that Q-conformal blocks of both the electric and the magnetic chiral algebra arise as partition functions of little string theory with defects. For the current purpose, the relevant class of defects are not the codimension 2 defects we studied before, but rather codimension 4 defects. So to describe this, let's, for simplicity, for now, take G to be simply laced. So G and its Longlands dual are the same. So we'll take little string theory associated to the simply laced Lie algebra G on M6, which is a product of C times R4, or C times C, two complex planes. So just as before, the same setup. The defects are strings supported at points on the Riemann surface and one of the two complex planes. Remember, the complex planes are were distinguished by whether you rotate them by Q or T. And in the present notation, we'll pick the plane that's rotated by Q. So let's take it to be the first one. Now, from the perspective of type 2B string on the 10-dimensional geometry, the defect strings on M6 arise from D3 branes, which are supported on 2 cycles in Y and a chosen 2-plane in M6. They're codimension 4 in 6 dimensions, so they're strings in M6. The insertion points of vertex operators are the positions of non-complex D3 branes on C. The class in Y that supports the D3 brane is the highest weight of the corresponding representation. Remember, we're we've decided to keep things simple and pick only fundamental representations. Now, the weight of the Verma module that one ends up computing, that one takes, is the Kalem modulus of y. It tells you the sizes of 2 cycles in y. So again, all the parameters are geometric. All the data is geometric. Now, the partition function of 6D little string with these classes of defects for generic lambda localizes to the partition function of the gauge theory on the defect. The theory on the defects is a 3-dimensional quiver gauge theory with n equals to 4 supersymmetry on C times a circle. Its quiver is based on a Dynkin diagram of G. The quiver group and the matter content are determined by the weight of the subspace of the Q-conformal block, are determined by the weight of the subspace that the Q-conformal blocks live in. Specifically, the framing data is determined by the choice of representations one studies, and the gauge group data is determined by the weight of the subspace. Now, the dimension vectors are the classes of 2 cycles in Y, which support the D3 branes. So the partition function of the 3D quiver gauge theory on the defect is computed by quantum K theory of the Nakajima quiver variety X. The Nakajima quiver variety X is the Higgs branch of the gauge theory. Quantum K theory of symplectic resolutions, including Nakajima quiver varieties, was developed recently by Okunkov with Maulik and Smirnov. Yes? Flavor symmetry. So right now we are just studying 2-0 string with D3 brane with defects which are codimension 4. So there's no flavor symmetry. There's no. We are not putting codimension 2 defects, not just yet. So there's no relation at all. We are only studying 2-0 little string on M6 with codimension 4 defects. So the theory that computes these 3D gauge theory partition functions was developed recently, and it's quantum K theory. And roughly speaking, what it does, it counts quasi-maps to X, where one works equivariantly with respect to the flavor symmetry group of the quiver, rotations. One typically studies it either on a disk or on P1, and then one works equivariantly with respect to rotations of the disk or the P1. This is this one. This is parameter Q. And an additional rotation that's associated with scaling of the symplectic form of X, and is associated with some R symmetry that these 3D gauge theories have. Now, the fact that quantum K theory computes partition function of little string theory in this geometry with 2-dimensional defects on C is analogous to the fact that the partition function of little string theory with 4D defects on C times C is computed by K-theoretic instanton counting. In either case, the theory grows a dimension because of the stringy effect. So it becomes 2-dimensional defects give you a 3-dimensional gauge theory on S1 times C. Now, the most basic object of quantum K theory, as studied by Okunkov and Maulik, is what's called the vertex function. The vertex function is actually a vector which counts quasi-maps from C to X. And the choice of the component of this vector has to do with the conditions that you impose. Because C is not compact, you have to impose some conditions at infinity of C. And that has to do with, that labels the components of the vector. In simple cases, one works equivariantly, so the infinity gets mapped to a fixed point in X. and the choice of that fixed point is the choice of the component. Now, the components of this vertex function of x turn out to be nothing but the doubly algebra Q-conformal blocks with degenerate field insertions. So remember, the doubly algebra conformal blocks that we need for the Longlands correspondence. To define these blocks, you still need to specify choice of contour of integration because the screening charges are integrals of screening currents. Now, there is a choice of contours of integration such that when you compute this integral by residue, you get the components of the vertex function. And again, like in the previous story with co-dimension 2 defects, the relation between k-theoretic count here of quasi-maps and the conformal blocks is simple and direct, as I just described. Now, let's turn to the electric side. A way to characterize conformal blocks of the affine Lie algebra is as solutions to Knizhnik's homological equation, where here x's are, if you don't remember this stuff, x's are the positions of the insertions of the vertex operators, and the conformal blocks have to be analytic in a chamber of parameter space, corresponding to how you take the insertion points to infinity. The deformation of this equation, corresponding to the quantum affine algebra, is a difference equation, the quantum Knizhnik's homological equation, which was discovered by Igor Frankel and Reshetikin in their foundational paper. Now, a key result from quantum K-theory, due to Malik and Okukov, is that the vertex function of x solves the quantum Knizhnik's homological equation corresponding to u h bar of LG hat conformal block. Remember here, G is simply laced, so G and LG are all the same. Okay. We've made that assumption a while ago. Now, more precisely, from the vertex function, by differentiating with respect to x's or placing additional insertions at the origin of the disk, remember we count quasi-max from the disk to x, one can generate a fundamental solution to the QKZ equation. That's what it proved. Now, the solutions that quantum K-theory provides for you for free are not themselves, even though they solve, you get a solution to QKZ equation, you don't get Q-conformal blocks of the quantum affine algebra. They're not Q-conformal blocks because the vertex function is not homomorphic in any one chamber of the parameter space. Instead, there is a linear change of basis depending on the chamber, such that V sub C, where C is the chamber, are holomorphic in the chamber and generate Q-conformal blocks. The change in this change of basis, what enters, these are not constants, they're elliptic constants. In other words, it's a linear operator which commutes with the difference operator of the difference equations. So it's a non-trivial thing. Now, the choice of basis you need to make to get QKZ conformal blocks turns out to have a geometric meaning. It is the elliptic stable envelope of the Nakajima-Quiver variety, which we recently discovered in the joint work with Andre. The elliptic stable basis is a basis in elliptical homology of X, which generalizes the stable basis in cohomology and K-theory due to Malik and Okunkov. So with elliptic stable bases in hand, we get an explicit map between Q-conformal blocks of the quantum affine algebra and the doubly algebra, which is what the conjecture, which is the statement of the quantum Q Longlands correspondence for the simply laced algebras. And you get it for any G. Now one can talk about extensions. So to extend this to non-simply laced groups where G and LG are not the same, one uses the fact that the non-simply laced Lie algebra can be obtained from a simply laced Lie algebra using an automorphism H of the Dynkin diagram of G sub 0. So for each non-simply laced Lie algebra, there is an associated simply laced Lie algebra with an automorphism. So specifically, this H acts as an involution of the Dynkin diagram. So from A, you get C, and so forth. This is familiar. From D, G2, and so forth. From D4, G2. Now, and this is how one would think about non-simply laced groups in string theory as well. So one starts by studying little string theory associated with a group of G sub 0 of which is simply laced on M6, which is C times the Riemann surface times R4, with a twist, which ends up permuting the nodes of the Dynkin diagram, whose effect is the same as permutation of the nodes of the Dynkin diagram of G sub 0. And you place the twist. Okay, this one gave up on us. We have another one. And you place the twist around the complex plane where the strings are. Remember, we were studying a little string on this geometry with defects that gave us insertions of vertex operators. So this implies a correspondence between Q-conformal blocks of the quantum affine algebra and the Longlands dual doubly algebra for non-simply laced G and LG should follow by generalizing the elliptic stable basis to, and Andre and Malik's result, to H equivariant setting, which should certainly be doable, one hopes. Now, another important generalization of the geometric Longlands program is to include ramifications. So this in principle should be a simple thing to do. Including ramifications corresponds to including d-fibrant defects from the first half of the talk. So these are defects that fill the R4 and are the points on the Riemann surface. So most of the story would go through with the relevant variety X, which is not holomorphic symplectic anymore, but is in an appropriate sense closed. It's a G-type Henshaw quiver variety, which is the Higgs branch of the three-dimensional n equals to 2 gauge theory on D3 branes in presence of D5 branes. The quiver gauge theories that arise have actually been studied, and also with me and Nathan, so they're well known, and the map is well known as well. Okay, so now, as Witten and Kapustin explained, the geometric Longlands correspondence is related to S-duality of n equals to 4 super Young-Mills theory. And of course, as such, deep understanding of geometric Longlands should come from deep understanding of S-duality. Now, many aspects of S-duality can be, as string theorists discovered in the 90s, can be understood within n equals to 4 super Young-Mills theory, or using the 6-dimensional theory X compactified on a 2 torus. So you can get far. However, to derive S-duality of n equals to 4 super Young-Mills theory, one can derive S-duality of n equals to 4 super Young-Mills theory from T duality of type 2B string on Y times M6, or with M6 containing a 2 torus. Or actually, all one needs is a little bit less. One needs a little string theory. So the fact that one is able to derive S duality of n equals to 4 super Young nodes from little string theory should explain why one is able to make progress on geometric Longlands in the context of this Q quantum Longlands correspondence. Okay, so that's all. Thank you.
Are there any questions?
Yes.
You take the quiver gauge cell instead. So what is the relation between them?
It's a different way of thinking about it.
Could you say a little more about this elliptic stable basis? And you mentioned elliptic cohomology. Did you mean TMF?
It's a long story. It's too long for an answer at the end of the talk. If you know, I don't know what TMF is. So.
Topological modular forms. When
No.
you said elliptic cohomology, I wonder what you mean by that.
There's a stable basis in cohomology that Okunkov and Malwick defined for a holomorphic symplectic variety, where so it's just a basis in classical cohomology of the manifold, where in the classical cohomology of the manifold, where manifold with equivariant actions on it, where to a pix, huh? So in the ordinary story, to a fixed point, you associate a cohomology class. In the elliptic variant of it, to elliptic cohomology class of the fixed point manifold, you associate an elliptic cohomology class of the full X.
So what do you mean by elliptic cohomology? That's what I'm trying to get at.
That's what we mean by it. So everything is equivariant. So it's a bunch of theta functions with geometric meaning. And if you want, let me give you perhaps a better understanding. There should be there's a way of understanding what the matrix element, what the elliptic basis is, as elliptic genera of certain two-dimensional gauge theories. Okay, so that.
How did the elliptic genera of two-dimensional gauge theories get in?
Aha, good. So the vertex functions, a partition function of a three-dimensional gauge theory on C times S1, with a certain set of boundary conditions. Okay. Now, what we'd like to do is change the boundary condition. Okay. The change of the boundary condition you can think of as a partition function of a three-dimensional gauge theory on T2 times an interval. Okay. And since everything is topological, we can shrink the size of the interval and get the elliptic genus.
Well, I have two questions, if I may. The first, I mean, when you say you have an explicit map between the Q Kac-Moody and QW conformal blocks, does it mean indeed you have explicit choice of contours for a given, choice of contours on the W side for a given element of a basis on the Kac-Moody side, the Q Kac-Moody side?
Yes.
Okay.
Well, they're linear. They're specific linear combinations.
Specific linear
combinations. To define, you see, to define, we have to define. I think the story of relation of little string theory to Q-deformed WZW and Q-deformed Toda theory suggests that there should be a good mathematical definition of what it means to be a Q-deformed conformal field theory. So there should be an a priori definition. Now, and I hope that people will work on it. Now, short of that, so yet you can say a smaller set of words if you're just interested in Q-conformal blocks of the double algebra, okay? They should be whichever definition one ends up with should be such that the double algebra conformal blocks, the choices of contours are such that you get the vertex functions of K-theory. So in a sense, quantum K-theory and three-dimensional gauge series of these defects provides for you a definition of what it means to be conformal blocks of Q-deform double algebra.
Okay, yeah, thank you. The second question is, I mean, the setup in which you were getting the Q-Kac-Moody symmetry or Q-Kac-Moody algebra, does it involve codimension 2 defects wrapping the surface C?
No.
No?
No. So you might ask what's the relation of this story to previous approaches to quantum Longlands, and it's different.
Okay, thanks.
So you mentioned insertions to be placed at the tip of the cigar to get the WCW conformal blocks?
Yes.
Can you characterize those insertions?
Well, yes. On one hand, you don't really need it, right? Because what you get, so what this procedure provides for you is a generator of the difference D module, right? So just by acting on it with difference operator, you will generate the entire set of fundamental solutions, okay? Now you can say, no, actually I want a little more than that. I want to get a canonical solution to QKZ equation in some preferred basis that Igor Frankel and Richard Tikin picked out. Can you give that to me? And the answer is yes, you can. Now, this is something that's known to Andre. There's a specific, the vector that takes from the canonical solution to QKZ equation to the vertex function is something called the capping operator. Now, you can try to get, okay.
Can those
So yes, for math purposes, it's known.
Can those insertions be precisely the thing that Jörg referred to in the last question?
I missed his talk.
No, his last questions now.
Huh?
His last question now. So he was mentioning the fact that to get WCW, often one needs a surface defect wrapping the Riemann surface.
No.
And I was wondering
Davide,
if it has
here,
related to
the way we get WCW from string theory perspective is perfectly understood. This is just, you see, the reason you need assertions, you open the tip of the cigar. As soon as you open the tip of the cigar, what one does is one studies the 2-0 theory on the Riemann surface times the cigar times C.
Yes.
Sorry, not the times the Riemann surface
boundary condition.
times the cylinder times C. Okay, yes. That is a canonical setting that.
Yes. But isn't that the same as inserting a defect?
Say Edward Witten showed that WZW models arise from the 2-0 theory.
Isn't that the same as putting a defect wrapping?
No,
Codimension 2 defects correspond precisely to opening up the cigar and putting
really.
the
In that, since it's just a theory on the cylinder, you have some choice, and string theory doesn't really tell you which particular choice you should put there. It's okay. Listen, these are explicit formulas, and we are talking about relation of a particular, something which is well defined mathematically to another thing which is well defined mathematically. And well, Edward is here. He can tell us if there's some direct relation between this and your approach with Stoyanovsky and Fagan. It's different.
Okay, in view of time, I would propose we close the discussion here and continue it in private. So let's thank the speaker again.